So in this video I'm going to show you footage of a sunset taken from 45,000 feet in an aircraft with the Theodolite app in my iPhone. As you can see, I have the crosshairs pointed at the sun, which is setting right on the horizon, and the app is indicating an angle down of 3.7 degrees. Now before I do, I just want to mention briefly this zero function on the app and why you need to avoid using it when you are conducting the observations or demonstrating the calibration of the app itself. So it's important when you're using this Theodolite app, and particularly when calibrating it, that you do not use that zero function in the bottom left hand corner. As you can see, it's grey at the moment. When it's active, it will be blue like that. Now let me just show you why. Currently, the app is calibrated correctly, and as you can see, as I move this phone up and down, the angle on the right hand side is responding accordingly. Now if I put the crosshairs right on the top of that second phone against the wall, you can see it's level. Now if I move the Theodolite app down to the base of that second phone, it is indicating an angle of negative 12.6 degrees. Now watch what happens if I hit the zero button. It just indicates zero, and it doesn't matter what angle that phone is. When I hit the zero button, it will just put the reading to zero. So it's important when calibrating and when using it not to activate that zero function. And the other thing to be mindful of when you're using this app in an aircraft is that you are pointing the crosshairs correctly towards the real horizon. This is one of my older videos where I saw the moon distinctly below eye level. It's just above the horizon, but below eye level. And we can also see very clearly in this video the Earth's shadow as the sun was setting. Now I had one flat earther come to my channel and insist that this line here was the Earth's horizon, which is absolutely not the case. The horizon was down here. Now, if you were performing this experiment and you were pointing the app crosshairs at this shadow line, you're not going to get an accurate reading. And the same problem can occur if you're flying above a temperature inversion where you have an inversion layer like this. As you can see, there is a clearly defined line, but that is not actually the Earth's horizon. There's another temperature inversion. You can see the haze is held in below the inversion and the sky is clear above that. And there's another indication of a temperature inversion. Now I know at least one flat earther has made this mistake when performing this experiment because he has the crosshairs on the app pointing at the top of a temperature inversion, and that is giving a reading to the top of the temperature inversion, not to the horizon of the Earth. And therefore it is a flawed experiment because he's not actually looking at the horizon. Now unfortunately, a lot of flat earthers have praised that video. They don't understand what they are looking at, and they have even mirrored that video. It is not an accurate measurement of the horizon because it's not even pointing at the horizon. And remember, as I have demonstrated previously, the window in the aircraft is not responsible for the horizon drop that we see. There is a test that I did in a hangar. Looking outside the left-hand window of the aircraft, you can see with an angle in the app of negative 2.8 degrees, the crosshairs are pointed just below that pipe on the hangar wall. Now when I moved to the door of the aircraft and set the same 2.8 degrees through the open door, you can see the crosshairs are in the same position. So the window is not causing the drop in the horizon or the position of the sun, as you will see later in the video. And I took the time recently to also demonstrate that from a car, where you can see the front window is clearly angled, but it does not change the position of the horizon looking through an open window or through the glass itself. The angle of the horizon position, as indicated by the app, does not change because of the angled glass. So in order to give you full confidence that my phone app was calibrated correctly, I positioned the crosshairs on the horizon line in the head-up display while we were flying. And as you can see, it is indicating level. So that means the phone app is correctly indicating true level, because the head-up display is a precision instrument that pilots use to accurately fly aircraft. It is calibrated accurately, and it is an instrument that is worth many hundreds of thousands of dollars. So that gives us the confidence that the phone app is giving us a good reading. I also move the app across to the eye alignment balls, and as you can see, when the line was in line with those three eye alignment balls, it is also indicating level. So again, that gives us the confidence that when I now point it towards the sun, and the sun is at a position that is more than 3 degrees below true level, we are getting an accurate indication. So once again, we have solid proof that the horizon does not rise to eye level, and it does in fact drop by the correct amount you would predict for a globe from 45,000 feet. Now, one final question I will leave with flat earthers. What causes the sun to set when I'm viewing it from 45,000 feet? When I talk to flat earthers, they talk about waves, they talk about mountains, they talk about irregularities on the Earth's surface, causing the sun to not be visible when it sets. From 45,000 feet, I am now looking out across water, and yet I see the sun setting. So there are no mountains, there are no 45,000 feet waves. What is causing the sun to set when seen from this altitude?